this lecture, I'm going to talk about one of the most important equations in the history of astronomy, which is called Hubble's Law. Obviously, you have heard of Edwin Hubble. You may not realize that, but of course the Space Telescope is named for this guy. Well, we obviously know that the Space Telescope is one of the most important scientific instruments that humans have ever built, and that it got named for this guy shows you how significant his work is, that we would name such an important telescope for him. Hubble studied galaxies. In fact, he was the first person to prove that there were galaxies outside our own. He was studying the distances to galaxies by using Cepheid variable stars. Talked about Cepheid variable stars in the last lecture as an example of a standard candle. And in fact, he was the first person who found Cepheid variables in the Andromeda galaxy, which is the nearest big one to us. And by proving that the distance to the Andromeda galaxy was bigger than the size of the Milky Way, he was able to show that the Andromeda galaxy was a galaxy all of its own and not just some nebula that was part of the Milky Way. Of course, what he also did that was even more significant was he discovered what we now know as Hubble's Law, which is a relationship between the velocity of galaxies and their distances. He didn't just figure out the distances to galaxies, he took spectra. He used the Doppler effect, found their redshift, and was able to calculate their velocities, just like we've done in class. And like any good scientist, he made a graph to see if there was a relationship, and in fact there was. So you've got velocity on the y-axis, distance on the x-axis, and it makes a nice straight line. And so if you think about the equation of a straight line, that's like y equals mx plus b. Well, v is what's on the y-axis, there's equals, distance is what's on the x-axis, b is obviously 0, and then there's the slope, which is this thing that we now call Hubble's constant. This equation, v equals h naught times d, is called Hubble's law, and it really is one of the most important equations in astronomy, because this is the basis of where we get all of our ideas about the origin of the universe from, and it's also where we get our ideas about the ultimate fate of the universe from. So in this equation, v is the speed of the galaxy. Now it's important that it's going to have to be in kilometers per second. That's an unusual unit, and you have to remember that you have to convert things to kilometers per second. The distance will be measured in units of megaparsecs. Remember, parsecs are a unit of distance that are about equal to 3 light years, and mega means times 10 to the 6th. So this is in millions of parsecs, and h naught is a number called Hubble's constant, and it's the slope of this graph. You'd think then that, okay, well, finding the slope of a graph isn't hard. Just, stick it in your favorite computer program and it'll tell you. Turns out that that is not such an easy thing to do. There's a lot of uncertainty in the measurements of the distances. We're not really good at finding distances to galaxies. We're getting much, much, much better now. But it's not something that's really well known, and that means that because there's a lot of uncertainty in this distance, that there's also a lot of uncertainty in the slope of this graph. So the value of the Hubble constant, h naught, is not really, really well known. Now, you can make a line of best fit, and we would usually say that the slope of that is the Hubble constant. In this example graph, they use light years instead of parsecs, and so the value that you come up with is 22 kilometers per second per million light years. If you convert that to parsecs, you get 68 kilometers per second per megaparsec. This is the best value that we have today. But because there is uncertainty in the distance measurements, there is uncertainty in the value of the Hubble constant, and so, for instance, just on this graph, you could come up with anything between 20 and 24 kilometers per second per million light years, and those would be equally good values. That sounds like a pretty big range, 20 to 24. You should be able to get it better than that. But This is better than what we did even as little as 20 years ago. When I was in graduate school, of course, we used the parsecs unit. They thought because of the uncertainties in the distance that the Hubble constant could be anything between 50 and 100. That's a huge range. And narrowing that down has been one of the biggest achievements that astronomers have had in the last 20 years or so. They were able to narrow it down because they started using white dwarf supernovas as a standard candle, and they were able to get much more accurate distance measurements. And so, as a result, we have narrowed it down to being about 68, but it could be as much as 72, it could be as little as 64, somewhere in that range. In a typical problem, I'm going to have to tell you what value I want you to use for the Hubble constant, because really this is not a 100% known value at this point. So I'm going to take you through a couple of example problems. This is number 1 in your packet. And this one's a pretty straightforward one. We have a galaxy that's moving away from us at a speed of 22,000 kilometers per second. That's v. And that's already in the right units. We want it in kilometers per second. And we're going to find the distance. Now, I didn't give you a Hubble constant here, so we're going to use our best value of the Hubble constant. That is 68. And we're going to find our answer in megaparsecs. I know my answer is going to come out in megaparsecs because that's the units that I see on the Hubble constant. And most of the time, the problems that I'm going to give you, you're going to do it in megaparsecs, but book problems, your book happens to like mega light years. So I can just do v equals h naught d, and so I have 22,000 equals 68 d. And I get an answer of a distance of about 324 megaparsecs, 324 million parsecs away. To give you a better sense of that, we'll convert it to light years. Now, 1 parsec is 3.26 light years. And we can also say that 1 megaparsec is 3.26 mega light years. So I'll do 324 megaparsecs times 1 mega light year per 3.26 mega light years for 1 megaparsec. And we get about 1,055 million light years. So over 1 billion light years away. That's the distance to that thing. Here's another one. This is more typical because it involves you have to use the Doppler effect from the last unit in order to get the speed. So we've got a galaxy with a redshift of 0.8. By the way, all galaxies, with the exception of a few, have a red shift, not a blue shift. They're all moving away from us. In the next unit, or in the next lecture, I'm going to talk about why they're moving away from us. So we've got a red shift of 0.8, and it asks what wavelength would we expect to find an emission line that normally occurs at 580 nanometers. So that's lambda naught. We're solving for lambda. From the last unit, we know that z is equal to lambda minus lambda naught over lambda naught. So 0.8 times 580. So lambda equals 1044 nanometers. That's a pretty big redshift. That takes something that's green light and turns it into infrared. Now, if the Hubble constant is 68, we want to know the distance to the galaxy. Well, to do that, I can use that z is equal to v over c. This will give me the speed. But that comes out in meters per second. That's not the units that I want. I need kilometers per second in order to use the Hubble law. So I need to convert first. So 1,000 meters in 1 kilometer. So that's 2.4 times 10 to the 5th kilometers per second. And now I can use V is equal to H naught D. And get a distance of 3,530 megaparsecs. Again, it's parsecs because the units that I used for the Hubble constant have megaparsecs. Whatever those units are right there, that's the unit of your distance.